All right, well, this is the first PSL demo day of 2021. We're excited to have Rick Evans from Rice University's Baker Institute of Public Policy here. Rick is a core maintainer of the OGUSA model, which is in the PSL catalog. And today he's going to demonstrate how to use that model through the Compute Studio web application. Rick, take it away.
All right, thanks so much. I put a link to my website in the chat. I'll try to be putting stuff up in the chat during this demo, but really happy to be here. Thanks so much for setting this up, Matt and Jason. I wanted to start off actually not on OGUSA, but just the policy simulation library community and highlight that there have been these demo days over the last few months, and I'm putting in the chat the YouTube channel for the policy simulation library where you can see, let's see, where you can see this is, I'm just sharing my browser where you can see different demos that have been done. Anderson Fraley did one on the tax calculator microsimulation model. I'll talk about that a little bit. That's something that's integrated into OGUSA that I'm going to demonstrate today. Jason did cost of capital calculator, a microsimulation model for firm incentives. And I just, this community of open source policy models, I just think is so important. And these models all have a ton of assumptions and a ton of variables. And I think for public policy, there's this philosophical imperative that these models be open so that people can see what exactly the analyst is doing, what are the assumptions underneath, and also so other people can verify results. And just one other screen I'll show is the policy simulation library GitHub organization, and let me put a link to that in the chat. But I'm sharing that on my screen. This, if one were to scroll down through this GitHub organization, you'd see lots of models. There's really developing a large, really nice community of people working together, putting open source policy models available for anyone to use and anyone to change and anyone to collaborate on. And so this, I've been a part of this community for about 7 years, and I just find it not only really fulfilling, but I think for policy analysis, it is actually necessary that these models be open. Another point, just in the current political climate in the United States where everything's supercharged and polarized, open source models are fundamentally apolitical. Like if somebody comes to OGUSA and wants to criticize me for any perceived political bias, I can just really point people to the model, say, why don't you criticize whatever assumptions in the model you think should be changed? And one thing, if someone were to look at all of these models, you see there's always ongoing updating and collaboration and adding new pieces to the model and fixing errors. And I've just found it to be a very fulfilling community. So I'm super proud to just demo OGUSA. Like Jason said, there's a model that he and I are core maintainers on, and I will jump into that now. So OGUSA, let me post in the chat where this resides on GitHub, where all the source code is. And I will just go to that page in my browser. A sec. But this OGUSA is a macroeconomic model. It is dynamic general equilibrium. It's an overlapping generations model. So this is a class of heterogeneous agent models. It does similar things to what some microsimulation models do. So it's got lots of different agents in the model and can have different firms and industries. And you can do experiments where you look at what's the effect of a tax policy change on different households, different industries, and you can see those changes over time. So microsimulation models do that as well. What the macroeconomic model does is it allows you to see how all those changes of where you're explicitly modeling individuals and firms, how those changes add up and affect the macroeconomy, how they affect GDP, wages, interest rates. Right now, a lot of questions I'm working on have to do with the national debt. And so these macroeconomic models, though, are much more complicated animals than a microsimulation model. As Jason mentioned, he and I are the core maintainers of OGUSA. I'd be remiss, though, if I didn't mention Kirk Phillips. He was a colleague of mine at Brigham Young University when I was there, and a lot of the early work on OGUSA has his fingerprints all over those, and he's at CBO doing great work right now. All right, so I've got the GitHub repository shared on my screen. And this is where all the code for the model is housed. There's some instructions in the README on the front page of how to install the environment for OGUSA and how to run it. But I want to go to, if I click on this link on the side, this is the documentation for OGUSA. And I want to make a point here. This is a Jupyter book, is the platform we use for the documentation for OGUSA. Open source and open science are both really important. That is, we share all of our code for the OGUSA model in this GitHub repository. And there's, if I were to click on one of the files, one of the Python files in this code, you see there's little doc strings in the file explaining things. In addition to that, you really need documentation that shows exactly what is in the model. And that for OGUSA is a pretty big task. I mean, this documentation I'm showing you in this Jupyter book amounts to hundreds of pages of PDF text. And we have documentation here for the API of the model, so you can go in and see what is actually in the code. And then we have documentation for the theory of the model. So things like, it shows all the equations of what comprises the OGUSA model, the characterizing equations. And so you see some of the math here. There's also, in this Jupyter book, you can see some of the code to execute figures. I think that's one of the nice features of this. But the equations, OGUSA really amounts to a really big set of nonlinear equations that have to be solved simultaneously, uses fixed point algorithms. So even just documenting the solution algorithm for this model is a significant undertaking. And that's something where, rather than just put the code on some GitHub repository or some website, you also need to explain the code. And I think this is something we're also trying to do a really good job on, but is always an ongoing process. So the documentation, let me just put a link to where this documentation is, so anyone can go to that if they want to. And one last thing I'll say before we get into actually how to run this on the web application. Well, two things, I guess. There's, in the documentation, one of the really nice features of OGUSA, if I were to click on this in the calibration section, how we calibrate the model, if I click on tax functions, one very nice thing with OGUSA is that it integrates another model. So it's a macroeconomic model, but to bring tax data into the model, it uses a microsimulation model, the one that Anderson Fraley presented in December, the last PSL demo day of 2020. We use that model to calculate tax rates, effective tax rates, marginal tax rates, fit parametric functions to those, and then we bring those functions into OGUSA. And that's described in this documentation. And this is something that you're going to see as I go through OGUSA, is that it can talk to other models, and it can use other models to get its tax inputs. It also can use other models to get its demographic inputs and other inputs. And that is all described in this documentation here. All right, so let me now go to what I want to share. So there's a way to run OGUSA just from the command line of your computer, and that's the richest and most detailed way to run OGUSA. What I'm going to present today is how to run this model on the Compute Studio web platform. So this is a platform I'm putting the link here to the page that I'm sharing in my browser. The platform that's been used in all the other PSL demo days demonstrations, where basically any modeler can post their model, and it can be run in the cloud with an interface that's very easy to use. That I like to say that Joe Sixpack can come on and run a policy experiment. So if I sign into this, and to follow me from here on, you'll need to sign up and have an account for Compute Studio. But if I sign into my account, the first page I'm going to come to is my page of all the simulations that I've run over the history of my account with Compute Studio. But I can also look over here on the left-hand side or up on models and see a lot of different models that can be run on Compute Studio. Some of those are subsidized, some of those are not subsidized, meaning some of those you might have to pay for your compute time. OGUSA takes a really long time to run. It's between 4 and 6 hours to run a policy experiment. And that's even highly parallelizing the computation underneath. And those runs right now are subsidized, are basically sponsored by the Open Source Economics Laboratory. So anyone can run those for free right now. Once that funding runs out, then you probably have to pay for it, and each run would probably be like, I think $3. I'd have to ask Hank Dupe, who runs Compute Studio. All right, so we want to look at OGUSA and how to do a run. So I'm going to click on PSL models, OGUSA, create a new simulation. So right at the top, you can see it says untitled simulation. I want to title this Evans PSL Demo Days Simulation, and let's call it an OGUSA simulation, even though that's obvious. This is helpful because it shows, these are going to be notes to anyone who uses this, and note up in the URL space of my browser. I'll just type this in, demo, I'm putting this in the chat, demo day simulation. That URL that I've posted in the chat, if I select, if you see this share button on the right, that's unlocked, that means this is public. So anyone can go to this simulation and see what we did and what the results are. And you could copy it, you could change things. And we're going to want to put some notes in of what we do. Well, maybe I won't put notes in. I'll show you after the fact the notes that I would put in. But then you start seeing down below this dark line a bunch of inputs to the model. And this is where we select what type of an experiment we want to run. What this is doing is OGUSA, like I said, is this giant system of nonlinear equations that models households and firms and government parameters, and then runs it all using a pretty sophisticated fixed point algorithm, and then gives the output. This web application is a way for a potentially non-expert user to come in, make some selections about what policy parameters and experiment they want to run, and then just hit go. So on the left side, under the black line, you see basically 3 sections of input parameters. You've got this top section that tells you what is the start year you want to look at, what data source you want to look at, and whether you want to solve for a full transition path or just the steady state. And then below, you've got some summaries of sections that are more detailed on the right. But OGUSA parameters, these are parameters that are modeled explicitly inside the dynamic general equilibrium model. And then you've got tax calculator parameters. These are parameters that get fed into the micro simulation model that gives tax data to OGUSA. And so I'll go through these 3 sections in detail, but for example, if I just went to OGUSA parameters and clicked on fiscal policy parameters, that would take me immediately on the right side to the fiscal policy parameters section. Okay, so let's not go there yet. Let's start at the top. I want to start with the year 2022, and I want to select the data source as the PUF, the public use file. This is the IRS public use file. This is actually a private file that Compute Studio has paid for to use and put on this site. Any user of the web application is not going to have this data ever on their machine, but it is protected on the Compute Studio servers for people to use for the tax analysis that we're going to do here. So I select the puff, and I'm going to click this reset button so that my run will use that new selection of the puff. And now I'm going to scroll through the right-hand side of parameters that I might want to change. You see behavioral assumptions. If I have any questions about a field, I can click on this I information button, and it's going to tell me this is the Frisch elasticity of labor supply. That's not super informative. But what do I want to do? There are open economy parameters, fiscal policy parameters. I want to change, let's see. I want to change the debt to GDP ratio in the initial period from 0.78, which is really kind of a 2019 number. I want to change that to 1.0 for 2022. And if I were really being honest, I'd put it to 1.1. Right? Debt to GDP is rising pretty rapidly in the United States. And then also there are some tax parameters that we can change directly in OGUSA that we will not be changing in the microsimulation model. Or rather, they're not available to change in the microsimulation model. Let's see what happens for this experiment if we increase the corporate income tax from 21% to 28%. This is a proposal of Joe Biden's to make this change. So we want to, let's put that in and see what it does. And then the final changes I want to make, if I go to the left side and scroll down to personal income, notice we're going to go on the right-hand side, we're going to go past all these other parameters that we can change in the experiments we're looking at. And I want to change the top 3 income tax brackets. So I want to change this 32% income tax bracket for incomes, this marginal tax rate on incomes between 170,000 and 216,000. Let's change it from 32% to 35%. Let's change 35% to 40%, and let's change that 37% on all incomes above 540,000 to 45%. So by the way, I need to say I'm not advocating this policy change, but this is similar to what the President-elect Biden has proposed, and it's an increase in taxes on higher incomes, and I think this is a great example to go through. So you'll notice there are a lot of different parameters I could change in this experiment. Any changes in these microsimulation model parameters, what they're going to do, let me go back to the OGUSA documentation. Think of these blue dots as for every total income amount in the microsimulation public use file data, there's an effective tax rate. When we change these parameters of the income taxes, this is going to change where these blue dots are. In particular, in these upper incomes, the dots are going to be higher. It's going to change the type of function we fit to those data. That's what's going to be happening with the interface of the microsimulation model to the macro models. We're going to fit a new function to the microsimulation data and then bring those new parametric functions into OGUSA. So those parametric functions are a summary of the more highly detailed microsimulation data. All right, so let's go back to our run. Once I've got all my parameters set on this input page of what experiment I want to run, I just go down to on the left-hand side to this green button, run, and I hit it. And the default is to make this experiment policy simulation public, and so I could click make private, but I want to leave it public, and I want it to email me when it's ready, because when I click run, it's going to say estimated time remaining 4 hours, and in my experience, it takes a little longer than 4 hours, so I definitely don't want to wait for this. But if I ever want to, I can always come back to this URL. This URL is now permanent that I've put in the chat, and in 4 hours from now, it's going to be done. So I have pre-run this, and the run that I did, I called it Evans OGUSA Simulation 3. And let's just look at the results of this policy. So notice what I did in this simulation. Not only did I give it a title, but I wrote down what I did for the experiment. And so that in the top of this simulation, you see the experiment that I did. We could look at the inputs to see exactly what I did, or we can look at the outputs here. This is, I want to focus on the outputs. We've got 10 more minutes. And so the outputs, the Compute Studio web application for OGUSA is going to give you just some default plots of some of the data. And so this first one is the percent changes in macroeconomic variables. And this is showing us what happens to GDP over the time path of the economy relative to the baseline. So GDP is lower in the initial periods up till about 2034, and then it actually gets higher than the baseline. So somehow this policy of increasing the corporate income tax rate and increasing taxes on the higher income tax brackets somehow increases GDP 15 years down the road. We see that there's aggregate labor. This blue line is lower than the baseline for the first 7 years, and then after that it's higher than the baseline. And there's this little blip here. That blip is interesting. That's just showing the expiration of some of the TCJA tax cuts in 2026. And so you see a little behavioral response there. Capital stock is decreasing for most of the time path up till about 2037, and then starts increasing. So one nice thing about this simulation is it shows that there is this cost, this reduction in output, this distortion from increasing taxes in the short run, but in the long run, there's some kind of effect that increases taxes. This is the crowding out. We can see that in this bottom plot that shows fiscal policy variables. So tax revenue as a percent of GDP is higher than the baseline. Obviously would expect to have more tax revenue. And debt to GDP is, after 20 years, is 8 percentage points lower than it would be in the baseline. So when I looked at this in the underlying data, instead of like 180% by 2042, debt to GDP is 172%. So this policy of increasing taxes reduces the trajectory of debt to GDP, and that actually creates less crowding out of investment. And so we actually see what this means of having GDP higher after 12 years is that after 12 years in the baseline, debt to GDP would be really imposing a cost of debt interest on household savings and income. And so this policy of raising taxes actually has some benefits in the long run.
Rick, this is Jason. I have a question. Why do these graphs have like a peak or a trough somewhere around 2041? What's going on there?
Yeah, 2042, there's this vertical line. This, in OGUSA, I guess the counterfactual is the best way to explain this. In these general equilibrium models, they have to be stable in the long run. And at current policy parameters, even though there's an increase in taxes, you can see that debt to GDP, you can't see it here. Debt to GDP is still going up under this proposed reform that we've done in this simulation, but it's going up less steeply. But if debt to GDP is going up forever, eventually the interest payments are higher than the income of the economy, and that the math doesn't work out. You can't pay for that. And so if that's going off to infinity, that's not a stable long run result. So this vertical line is a point, we call it a closure rule, when a rule needs to be implemented to stabilize the economy. And in OGUSA, the default is to stabilize the economy, the debt to GDP trajectory at some percentage. And that percentage is 200%. That's a really high place to stabilize debt to GDP. But that's implemented by increasing, you can see this down here in this bottom plot, that's implemented by increasing government spending in that 2042, and then changing government spending gradually to slowly bring debt to GDP into line with this 200% long run level. So this vertical line, there's something fundamentally changing. It's a closure rule. the alternative would be to do a model that does not have to be stable in the long run. And in some linearized models, you can get away with that, but it seems not realistic to me. And more realistic to me is that once debt to GDP gets way out of whack, you get a Greece or a Portugal type event where basically the regime has to change and some policy changes have to be made. All right, thanks for that question, Jason. Another question?
Yes, you could stabilize debt to GDP or debt per person at the level it reaches in 2042. Then you wouldn't have these weird changes after 2042. Then you would have basically have a straight line afterwards.
Yes.
Is there a particular reason why you choose 200%? I mean, that seems like...
No, it's just a default, but
arbitrary.
That's actually a great question. Let me go back to the inputs and just show you, Felix. There's actually, this is an assumption you can change in the input parameters, and it's in the fiscal policy parameters. So you can choose the period, the number of periods after which you start implementing a closure rule. You can push that out further. You can choose the number of periods after which the economy is just, government spending is changed, has a very hard change in order to set the debt to GDP ratio exactly at that long run level. And then right here in this box, you can set the debt to GDP ratio that should be achieved in the long run. So here it's set to 2 or 200%, but we could set it to 1.5 or whatever it is in 2042. Now, there's a ex ante, we don't know what that level is going to be. We actually have to run the model to know what that's going to be, but you could run the model a couple times. And this is a discussion that Jason and I have had with the Tax Policy Center, where in the simulations that they do, that we do with them, they really want that closure rule to look as little jarring as possible. So actually choosing a long run debt to GDP ratio that's pretty close to where it ends up when that closure rule starts being implemented was important to them.
Yeah, I mean, you can, so we do that without much work by just stabilizing the debt per household level. And so basically debt per household then stays constant after once the closure rule kicks in. And that means that, you know, after some adjustment, all the lines going to be level. They don't change anymore.
Yeah, so what we found is that that closure rule, when and how you implement it matters. There's actually a paper out by Brandon Pecoraro and oh God, what's her name? How did I forget her name? Rachel Moore at
JCT.
At the JCT, looking at the effect of these closure rules. And I think that what we try to do with this closure rule is have as little jarring effect, the most gradual effect as possible, so that the results of the model in the first few years after the closure rule starts being implemented are as affected as little as possible. So I'm running out of time. Let me just say two more things before we finish up, because I think we've got a hard stop at noon Eastern. With this output, this table and these plots is a very small subset of the full results. You can click download results and it's going to give you a spreadsheet that has more data in it. So let me just show this spreadsheet. This spreadsheet has the data series, not just in percentage deviation, but in the actual levels, where you've got GDP by year, and you've got it for the full 300 years of the simulation, aggregate labor, government spending, expenditure, government debt, just as a level. And so you could create your own plots from that. I will say that spreadsheet output is also a subset of the full output of the model. And if you really want the full output of the model, you need to run it in the command line on your local machine, which is something that Jason and I do on a regular basis. It takes a little more work, but I think we've got some good documentation of how to do that in the OGUSA documentation. So let me just open it up to if there's any more questions. I think we're close to the end here.
What optimization routine do you use to parallelize this code?
So those are two questions. We're using a root finder in order to solve the system of nonlinear equations in every period. And then we're using the Dask package in Python to parallelize that optimization. So you've got, in every period, you've got more than 500 nonlinear equations that need to be solved, and we're breaking those up into groups of 7, and then we're breaking those up across the time path.
And what is that root finder?
That is a good question.
Is that documentation here?
I don't know if it's in the documentation, Felix, but I can give that to you offline after this call or after this demo. I just don't think I can find it quick enough. I'm just gonna have to go into the code and pull that up.
All right, thank you.
Thank you for those questions, Felix, and thanks everybody for participating in this.
Rick, thanks a lot.
All right. Thank you, guys.
Have a great day.
Thanks, Rick.